Welcome. In statistics, we talk a lot about probability distributions, and there are many different kinds, but there's one particular kind we talk about more than any other, maybe more than all the others put together. So many things follow this distribution naturally, it's pretty much indispensable. In fact, we've taken to calling it the normal distribution. But where does it come from? Why this particular shape? Why is it so common? We can get some important clues if we look at something that is random but not the normal distribution. Let's flip a coin. We'll score 0 for tails and 1 for heads. Here's the probability distribution. A 50% chance of 0, a 50% chance of 1. That's certainly not the normal distribution. If we flip 2 coins, we could flip both tails and score 0, or we could flip both heads and score 2, but it's more likely we'll get one of each and score 1. Here it is if we flip 3 coins, or 4, or 5, or more. An interesting thing is happening. As we flip more and more coins and add up the individual coin flip scores to get a total, the probability distribution of the total is taking on a characteristic shape, a very particular bell curve shape. Let's roll some dice. We'll start with just one die. We can get any of the numbers from 1 to 6. Here's the probability distribution. It's definitely not the normal distribution. If we roll 2 dice and add them, it looks like this. Here's 3 dice, or 4, or more. Once again, an interesting thing is happening. As we roll more and more dice and add them up, the probability distribution of the sum is taking on a characteristic shape, the same shape we got with coin flips. It's almost as though, simply by virtue of being a sum, their probability distributions are approaching this sort of universal shape. Well, that is exactly what is happening. The probability distribution of the sum, be it for coin flips or dice rolls or whatever, is converging on the same shape, a universal shape. Incidentally, this doesn't just happen for sums. The same thing happens for averages that happens with sums. Let's put the whole thing in more formal terms. Suppose we have a random variable x. We can take many samples of this random variable, and with those we can form a sum or an average. The most powerful theorem in all of statistics is the central limit theorem. It says that no matter what probability distribution the data may follow, if we take many samples and form a sum or an average, the probability distribution of the sum or average will converge on a universal shape. That universal shape is called the normal distribution, and that is where the normal distribution comes from. It is the universal shape that the probability distribution of sums and averages will converge on. By the way, there is one caveat. There are some exceptions. The original data does have to follow a probability distribution which is well behaved, meaning it has a finite mean and standard deviation. That's the case most of the time, and in most cases the central limit theorem applies, and it leads to the normal distribution. There are many different normal distributions, but let's start with the standard normal. That's where the mean value is equal to 0 and the standard deviation is equal to 1. The mean value is usually written as the Greek letter mu, the standard deviation as the Greek letter sigma. When these conditions are met, we have the standard normal distribution, and it follows this simple equation. If we make a graph, well, we've seen this shape before. What makes it standard is that the mean value, this central point, the balance point, is equal to 0. And this standard deviation, which is related to the width of the distribution, is equal to 1. There are, however, normal distributions that are not standard, where the mean is not 0, or the standard deviation isn't 1. They follow a more complicated equation that has 2 extra parameters, the mean, mu, and the standard deviation, sigma. The mean has the effect of shifting the distribution left and right. The standard normal has a mean of 0. If we change the mean to 1, we get the same distribution but shifted to the right. If we change the mean to 8, we get the same distribution again, but shifted even further to the right. The standard deviation appears twice in the equation, once up top and once down in the bottom. Up top in the exponent, it widens the distribution. If the standard deviation sigma is equal to 10, the whole graph is 10 times wider. Down at the bottom in the denominator, it shortens the distribution. If sigma is equal to 10, the whole graph is only 1/10 as tall. Since the widening factor and the shortening factor are the same, they cancel each other out, and the area covered by the graph remains unchanged. Here's the standard normal. It has a standard deviation of 1. If we increase the standard deviation to 1.5, it gets wider. It's 50% wider. It also gets shorter. It's only 2/3 as tall. If we increase the standard deviation to 2, it is twice as wide as the standard normal, but it's only half as tall. Because we can change the mean and the standard deviation, there are a whole family of normal distributions. There's the standard normal. There's another one with a mean of 2 and a standard deviation of 3. Here's one with a mean of 5 and a standard deviation of 1.5. Here's one with a mean of -6 and a standard deviation of 2. Any choices for mean and standard deviation are allowed, except the standard deviation has to be positive. It can't be negative or 0. After all, you can't have negative width, and you can't have 0 width. Because the widening and shortening factors are the same, area is preserved, so the area covered by this one is the same as the area covered by this one, the same as the area covered by this one and by this one. Let's take another look at the dice rolls, but we'll start with the standard normal distribution. Then let's add the probability distribution for the total you get if you roll 20 dice. Let's take the standard normal and change its mean value. Shift it over until it matches the dice rolls. Then let's increase its standard deviation to widen it. It'll shorten at the same time until it matches the dice rolls. When the parameters match, we find that the fit is outstanding. The probability distribution of the total of 20 dice really is converging on this particular shape, the normal distribution, with remarkable accuracy. We've now learned a bit about the normal distribution. For one thing, and perhaps most important, we found out where it comes from. The normal distribution is the universal shape describing the probability distribution for sums or averages. It can have any location, any mean value mu, and any width, any standard deviation sigma, except that we require the standard deviation be positive. And because there are so many choices, there's a whole family of normal distributions, one for each mean and standard deviation. We did pay some particular attention to the special case when the mean is 0, the standard deviation is 1. It's called the standard normal distribution. There's a whole lot more to learn about the normal distribution. It's one of the most interesting and definitely one of the most useful of all. But don't worry, we'll be talking about that plenty because it is, after all, the most talked about distribution in all of statistics.